In this set of notes, we're going to start looking at variable selection. So oftentimes we may have a data set with many independent variables, and if we try to fit a complete second order model, the number of parameters gets very large very quickly. So in this module, we're going to look at what are called variable screening procedures, and they can be used to objectively determine which independent variables in a list are most important predictors of Y. Now, one caveat with this is not something that we do all the time, and even if you do a variable screening procedure, this is not something that is necessarily set in stone. And so what I mean by that is if you were collaborating with someone and they tell you, I am specifically interested in this variable, and let's say they had a list of 10, but there's one of the 10 that they for sure, they want that one in the model, they know they're interested in it. If that variable doesn't come up in the variable screening procedures, that doesn't mean you necessarily throw it out. So this is just one component when it comes to model building. We also have to listen to our collaborators, what they're interested in. There's a lot of pieces that are going on, and so this is just one tool. So the first type of variable selection we're going to look at is what is called stepwise regression. The stepwise regression procedure is one of the most widely used in variable screening methods. And so to do stepwise regression, we use these 3 steps. So the very first thing we do is we fit all the possible one variable models. So if I had 10 potential variables, I would fit basically 10 simple linear regression models. And then I would choose the independent variable x that has the largest absolute t-value. So again, if I had 10 independent variables, I would fit 10 separate simple linear regression models. For each of those simple linear regression models, I would look at the t-statistic on the slope, and then I would choose the model that had the highest one. So next I would search the remaining k-1 independent variables for the best 2 variable model. So now what I would do again is I would fit 10 different models, but I would retain that original variable that I selected. Sorry, I would fit 9 models rather, not 10. I would keep in the model the one that I had already selected, and then I would look at all the potential 2 variable models. So for example, let's say I decided to keep variable 5. What I would do is I would look at the model that has variable 1 and variable 5, 2 and 5, 3 and 5, 4 and 5, and so on. Then what we would do is go back and make sure that the t-value for the first beta is still significant. If it's not, then a search is made for an independent variable with a beta parameter that will yield the most significant t-value in the presence of the x2 variable. And then we search the remaining k-2 independent variables, and we basically repeat the process over and over again. So this is an iterative process. We're not going to do this by hand. This is an iterative process that software does for us. And the result of this procedure is a model containing only those terms that are significant at a specified alpha level. When we work with stepwise regression, the usual criterion for including or excluding variables is alpha equal to 0.15. So notice this is different. A lot of times we see alpha equal 0.05. That's, for a different scenario, a different hypothesis test. So this, for stepwise regression, we generally use alpha equal to 0.15. Now, one thing you're going to notice in this note set, if you haven't already, it's pretty long, and the reason for this is we are going to get a ton of output anytime we do one of these variable selection procedures. So majority of this note set is going to be output. So let's look at an example. So this one comes from Mendenhall 2012. We have an international management consultation firm has developed a unique and interesting application of multiple regression analysis. Many firms are interested in evaluating their management salary structure, and what they did was they used multiple regression models to accomplish the salary evaluation. The compensation management service measures both the internal and external consistency of a company's pay policies to determine whether they reflect the management's intent. The dependent variable Y used to measure executive compensation is annual salary. So in other words, our predictor variable is going to be, or not our predictor variable, but our response variable rather, is going to be annual salary. And a preliminary step in the construction of the multiple regression model is the determination of the most important independent variables. So here in this table we have 10 potential independent variables. Notice if we were to complete a complete second order model with 10 independent variables, we would have a massive model. So instead what we're going to do is we're going to use stepwise regression to decide which of these 10 should be included in the building of the final model. So these 10 variables, once we perform selection, we're not going to get a model from this procedure. We're only going to find out which variables are the most important. Alright, so if we run this in SAS, the next several pages are going to show each of the iterative steps for the stepwise regression, and so we're going to look at each of these. So we're going to start out with step 1. So remember in step 1 what stepwise regression is going to do is we have 10 variables, so it's going to fit 10 different simple linear regression models, and then it's going to find of those 10 simple linear regression models which of the slopes had the highest t-test statistic. And so in step 1, once this was done, SAS found that the first variable, so if we go back up to our table, that is experience. So experience was the most important variable. It had the largest absolute t, and so it is maintained in the model. So next we go to step 2. So in step 2, SAS is going to retain x1 in the model, and then it's going to fit all of the possible models with x1 and one of the other variables. So for example, it will fit x1 and x2, x1 and x3, x1 and x4, and so on. And in doing so, the model that was, or the variables that were selected rather, so x1 was retained in the model, and x3 was now added. This process continues to step 3. So this time it's going to retain x1 and x3, and it's going to test all the possible 3 variable models. So it's going to test x1, x3, x2, x1, x3, x4, x1, x3, x5, and so on. And then remember, there's always the possibility that it would go back and take x1 and x3 out of the models if need be. In this case it didn't. The variables selected this time were x1, x3, and x4. This process continues, so we are now on step 4. In step 4, SAS added in the 4th variable. Here we have step 5, and again the same process continues, and now you'll see we have x1, x2, x3, x4, and x5. Now, the fact that these are in order from x1, x2, x3, x4, and x5 is just coincidence. It just happened that these were the 5 that get maintained in the model. Completely possible had we reordered what those variables were that we might end up with x1, x2, x3, x7, and x8. And then, SAS actually stops at this point because notice it says no other variables met that alpha level, so entry into the model. So SAS has determined that x1 through x5 are the 5 most important variables in the model. And again, the fact that it picked 1 through 5 was just coincidence for this example. The important thing here is it has chosen a subset of 5 variables from our original 10. And so this is what stepwise selection would suggest would be the 5 most important variables are. And then from here we can continue on with the model building process and determine if we needed any higher order terms, if we needed interactions, and so on. There are additional stepwise regression techniques. They are what are called forward and backward elimination methods. They are similar to stepwise with some differences. The forward selection is exactly the same as stepwise, with the exception that once a variable is included in the model, it stays in the model, so we never potentially remove variables once they are in. Now remember, with both forward and stepwise, we start out by looking at all of these simple linear regression models. Backwards does the opposite. It begins with all k variables in the model. So with our previous example, we had 10 predictor variables, so it would look at the main effects model with all 10 variables in it, and then it drops the variable with the smallest t-value. From there it would fit the model with the k-1 variables and drop the variable with the smallest, and this would continue until all variables have sufficiently large t-values. And then again we're going to use that criterion of alpha equal to 0.15 is the one that is typically used. So let's look at some examples of the output of both forward and backward elimination with that previous example that we just looked at. So here is the SAS output. Remember that we had 10 different predictor variables. So in backwards elimination at step 0, all variables are entered into the model. And so we can see here in step 1, we do have would be that main effects model with all 10 predictor variables. So in step 1, the very first thing we're going to do is we are going to eliminate one of the variables. So if we look through here, we can see that variable x10 was the one that was removed. So let's go back to step 0 and look at the fitting of that main effects model, and let's look at the different, in this case it is f values, but if you wanted the t values you could just take the square root of each of these. So the smallest f value would be the same as the smallest t value. Notice that the variable with the smallest value is x10, so it makes sense that x10 was eliminated in step 1. So here are our new variables. So notice we've now got a main effects model with x1 through x9, and again we can predict which one is going to be removed in the next step. Notice that the one with the smallest value for the test statistic pardon me, is x7. So since x7 is the smallest, we would anticipate it to be the next one removed in step 2, and we can see in backwards elimination step 2, x7 is the one that is removed. So this process continues. We refit the model with the new 8 variables. The one with the smallest test statistic will be removed. So we can see in this case it is going to be x8. And we can see in step 3 x8 was the one that was removed. So this process continues. And you can look through these on your own through the different steps. Notice once we get down to, we're currently in step 5. Step 5 has x1 through x5 left in the model, and we can see that all of these are significant. So the backwards selection stops. All variables left in the model are significant at the 0.15 level. And so we can see here in a summary of the backwards elimination, we first removed x10, x7, then x8, x6, and x9, which left us with this model right here. Next, we can look at the output from forward selection, and again this is going to look very similar to the stepwise. In step 1, we're going to fit the model. We're going to fit the separate simple linear regression models with all 10 and look for the one that has the highest test statistic. So we can see in forward selection in step 1, x1 was the first one selected. In step 2, we see that we added on x3. In step 3, we added on x4, and this continues. And this output, again, is going to look very similar to the stepwise regression, and we can see in the summary of the forward selection, we actually ended up with those 5 variables. So for this particular example, whether we use stepwise regression, forward elimination, or backwards elimination, we actually end up with the exact same 5 variables. And so in this case, we do get the same results from all 3 methods. That will not always be the case. It is possible that the different methods will result in different variables. And so this is one of the hard things about variable selection, is you don't always necessarily get the exact same output from the different methods. So often people will make an argument for a particular method before they ever do the variable selection and say, this is the method I plan on using, and then they use that method and see what comes from it. It would be a bad idea to use several different methods and then say, well, I liked the output from this one the best, so that's the one I'm going to go with. More you want to argue the method first, then apply it. Alright, so one other possible way that we could look at is what is called all possible regression selection procedure. So since we have more powerful computing methods, in other words, we have better computers, we can also do what's called an all subset selection method, which gives limited output from fitting each possible model. So the all possible regression selection, this one will we can actually put actual models in, not just variables that we're interested in. This is a more subjective approach than stepwise regression, and there are several different criteria that could be used to choose which one is the best model. You all in Mini Project 2 actually already did something somewhat similar to this, because I asked you to look between 3 different models and argue for which one was the best. So the first thing that you did was you looked at those nested f-tests, you determined, do we actually need these interaction terms, because you saw that the two-way interaction model and the main effects model were nested in the three-way interaction model. And then if you did need those terms, the next thing you did was you looked at R squared and you said, okay, is R squared similar for the 3 models, or am I really getting gains by including these higher order terms? And so in other words, you use the coefficient of determination to do some basic model selection. So here we're going to talk more about this value and how we could use it in more complex scenarios. So what I would like you to do is this next section, I'd like you to pause the video and I'd like you to read about these different criteria. So there's several different criteria that we could use when it comes to model selection and determining which model is the best. So pause the video and read through these different criteria. Alright, so next we're going to see how to actually apply this and what this would look like. So this example comes from the Perez textbook. So table 5.1 presents the results of different linear regression models to explain blood triglyceride as a function of waist circumference, hip circumference, high density lipoprotein, cholesterol levels, and age. So notice we've got multiple predictor variables, so there's lots of different models we could look at. So looking here, we've looked at several different models. So let's kind of break this table up. So the first thing we do is we look at the possible one variable models. So in other words, these are going to be 4 different simple linear regression models. Next, we look at the possible 2 variable models, the possible 3 variable models, and the possible 4 variable models. Now notice here we're still not including higher order terms, but we could do that. So if we look through here, we can use these different criteria to help us pick which model is the best. And in general, same as when we talk about whether we're going to use stepwise, backward, or forward, we would want to pick prior what method we're going to use to evaluate our model. In other words, which criteria, because it might be that all the criteria do not agree with one another. So if you think in terms of, writing a paper, again, you determine what methods you're going to use first, and then apply those methods to the data to see what the results are. So let's look at some of the different potential values. So we started off looking at R squared, and we know that we want high R squared values. So for example, if we look through here, we notice there are several models that have R squared close to 0.8. Now one thing that we have to keep in mind though is that every time we add in a new variable, R squared is going to increase slightly. So it's no surprise that the model with all 4 predictors has the highest R squared value. So often when you're working with multiple linear regression and you have more than one predictor and you're comparing models, you want to use the R squared adjusted because it's going to slightly adjust for the fact there are more predictor variables. So notice what happens to our R squared values for all of the ones that have that R squared in the 0.8. We see that for this single variable model with waist, we get a very similar R squared adjusted. But if you look down to the model with all 4, the R squared adjusted actually now dips into the 0.7. So using this criteria as we look up, we can see that all of them have dipped down slightly, but the model with all 4 has dipped the most. So now if we look for the ones with the highest R squared, we could look for R squared that were around 0.79, and we would see that really, we're losing percentages for some of those higher ones. Now when it comes to Mallow, CP, AIC, and BIC, remember that we want the lowest value. So that's different from R squared and R squared adjusted. We now want models that have low AIC and BIC. So looking through here, the low values for AIC are going to be around 170. And for BIC, our low values are also going to be closer to 170. So we can use this to help us pick our model. And looking at this, it appears that we probably don't need all 4 variables, but really some combination of 2 of the variables, or maybe even 3. So again, the idea here is we're using this for variable selection. We could then go from variable selection onto model selection. So I'm going to add to these notes here at the bottom. So instead of references, you're actually going to see a section called caveats. And it's just going to state that there's a reminder that you should not use either any of the stepwise procedures or the all possible regression procedure to determine the final model for predicting Y. It really is just there to help you pick out what variables or combinations of variables might be useful. Part of the reason for this is that these procedures conduct an extremely large number of tests, so the probability of at least one type 1 or type 2 error is going to be extremely large. Usually higher order terms such as interactions, quadratic or cubic variables are not included in the variable screening procedures. So all the examples that we've looked at, we've only looked at main effects. Therefore, the final model will be a first order model if we just use these methods, which is usually not realistic in most real world relationships. And even if higher order terms are used in the variable screening procedures, most times the model chosen by these methods is nonsensical, and so because of this it won't result in a hierarchical model. And so what we mean by that is this method might suggest to include the third order term but none of the main effects, and we know we can't do that. If we include a higher order term, we also include all of the lower level terms. The other problem here is we have to be very careful with categorical variables. We've seen that categorical variables we will often dichotomize. So if I have a categorical variable that is represented by 3 indicator variables, I would have to be very careful in how I do this variable selection and make sure that if I've used dummy variables that I write the code the correct way so that all of them would be incorporated if one of them is incorporated. And then the big thing is, we want to make sure that we don't abandon common sense in selection. Some important variables may affect Y in terms of interacting with others, and this is often looked in the variable screening methods. So we really just use variable screening for their purpose, which is variable screening. We don't use it to say this is going to be our final model. It's just to help guide us in the direction of building our model. And once we have an idea of what variables are important, then we can use some of those methods that we looked at previously in terms of, fitting models with some of those higher order terms, using our nested F test to help us learn, do we actually need those higher order terms, and so on.